Hello everyone, my name is Vahe Amdilian and I'm going to be talking about 5.1 linear models. Chapter 5.1, section linear models. This section includes mass spring systems such as free undamped motion, damped motion, driven motion, and also circuit LRC systems. The problem that we're going to be looking at focuses on many different types of systems. Hooke's law is also considered, as well as Newton's second law of motion. The problem that we're looking at is problem number 4 under 5.1. It states that a mass of 4 kilograms is attached to a spring with resistance of 40 times the velocity. A states that find the value of the spring constant K so that the spring is critically damped. B asks to find a motion if the spring constant is at 84 given the parameters, along with sketching it with C. D also asks to find the motion at a higher spring constant K with the given parameters, and we're also told to sketch that as well. So we're given a general spring equation, md squared x over dt squared plus 2 lambda dx over dt plus omega x equals function t. Also, the book writes it as r instead of the 2 lambda, but it's better known as beta or beta over m. So we have our md squared x over dt squared, which is our mass value. Our beta dx dt is our damping force, along with the spring constant, omega x, or better known as k, and our driving force, which is a function of t. So what's given in the problem? We have mass, which is at 4 kilograms, beta is at 40, and it also states if it is at critically damped, which we can assume is lambda squared equals omega squared. There's a little graph at the bottom. It's a little example of how critically damped is. It's kind of in between overdamped and underdamped, which on the right we can see overdamped is lambda squared greater than omega squared, which is non-oscillating, compared to the underdamped lambda squared less than omega squared, which is an oscillating graph. So for A, it states that if it's critically damped, so we're assuming that lambda squared equals omega squared per the equation, and it's also better known as 2 lambda equals beta over m. And given the parameters of beta 40 and mass at 4 kilograms, 2 lambda is equal to 10. Once we divide out the 2, lambda is equal to 5. So given the actual parameter of 5 being lambda, we can plug that back into the equation. 5 squared is equal to 25. And omega squared is better known as spring constant over m, which m is 4. We're trying to find the spring constant. So we get rid of 4 on that side. We get a spring constant of 100. For B, it actually gives us the spring constant given the parameters with x prime equals to 1 as the velocity. And per the equation for the spring general equation, we can plug in the numbers as 4 for mass, beta for 40, and given the spring constant of 84. And we turn that into the auxiliary equation of 4m squared plus 40m plus 84. And once we divide out 4 from the equation, we get a 1 coefficient at the front. So we can easily FOIL that out to m plus 7 and m plus 3, which we get m equals to negative 7 and m equals to negative 3, which helps us out for the general solution, as we get x of t is equal to c1 e to the negative 7t plus c2 e to the negative 3t. So use that equation And we also have our x of t prime to the right of that, as we're going to use that equation in a second. So once we plug in 0 for x of t and 0 for t, we can minus out the e to the 0. So that will be 1, which will give us 0 equals c1 plus c2, or better known as c1 equals negative c2. So for x prime equals 1, we can plug that into the second equation that we just said. And once we have e to the 0, we can cross that out and put 1, which will equal to 1 equals negative 7c1 minus 3c squared. So since c1 equals to negative c squared, we can plug that in to that equation, 1 equals negative c1. And we get the equation of 7c to the second minus 3c to the second. And we get c2 basically equals to 1 over 4. So divide that out. And since c1 equals to negative c2, you can see that c1 equals to negative 1 over 4. Which helps us to write the actual general solution of x of t, negative 1 over 4 e to the negative 7t plus 1 over 4 e to the negative t. And trying to sketch it out, we can see that lambda squared equals to omega squared. And omega squared is the spring constant over the mass. Just plug in those numbers, we divide that out, you get the omega squared is equal to 21. And since 21 is less than 5, 25 is greater than 21, we can see that it's an overdamped non-oscillating graph. So for D, it gives us the spring constant of 116. The given parameters x prime equals 1 as the velocity. So we have the spring general equation. We plug in our numbers once again. We turn that into the auxiliary equation, 4m squared plus 40m plus 116. And once we divide out the 4 from the equation, we get a coefficient of 1 at the front. And since we couldn't easily FOIL this one out, we had to enter that into a quadratic equation. We had a equals 1, b equals 10, and c equals 29. And so once we plug everything in, we get a negative inside inside of the square root. So we got m equals negative 5 plus or minus 2 of I. And that helps us with the general solution of c1 cosine 2t e to the negative 5t plus c2 sine 2t e to the negative 5t. And so once we have that, we can plug in our numbers. X of t is 0 and 0 for t. And so we can see a lot of things just cancel out. And as everything cancels out, we have c1 equals to 0 since the cosine of 0 is 1. That's the only thing that really stayed. So that c1 is 0. So for the x prime, we also plug that into that long equation. A lot of things get canceled out because e to the 0 is 1. Cosine is 1, cosine of 0 is 1, sine of 0 is 0. So we're left with a solution of 1 equals to negative 5 times 0 plus 2c squared. Since we got c1 at the top equaling to 0, we can easily say that c2 is 1/2. So it helps us with the general solution of x of t is 1/2 sine 2t e to the negative 5t. And E asked us to graph it. So we go ahead, lambda squared equals to omega squared. And per the equation of spring constant over the mass, 116 divided by 4 is 29. So if 29 is our omega, it's gladly over the spring, the lambda squared. So we get an oscillating underdamped graph